All right, time to review for test 3. In problems number 1 and 2, we're asked to approximate the number using a calculator and then also to round to 3 decimal places. So we'll look at number 2. So 2 raised to the square root of 6. If you haven't located the square root key on your calculator, oftentimes it's above another key, another button. So where I see x squared, I'm going to hit the second key and the x squared, and then I can insert 6. 3 decimal places would be 5.462. Okay, I'll leave number 1 for you. You can check the key that's posted online for the correct answer. Problems 3 and 4 ask us to graph the given functions by making a table of coordinates. We're told what x values to use. So I'll go ahead and work through number 4, leaving number 3 for you. So everywhere I see x, I'm going to replace it one at a time with each of these x values. Now you can certainly enter this into the calculator, but I do remember if I want to make this exponent positive, I could reciprocate this fraction that's in here, make it 2 over 1, which is just 2, and adjust to a positive exponent. All right, we're going to try and graph f of x equals quantity 1/2 to the x. This is an exponential function that doesn't grow, but it decays. So plotting each of these ordered pairs. Okay, there should be enough points for us to kind of get the basic idea of what this exponential function looks like. We want to be kind of mindful about how to graph it. It goes off the screen this way. Okay, what we have is a horizontal asymptote at y equals 0. All right, for 5, 6, and 7, we're dealing with graphing exponential functions and transformations on those parent functions. So for problem number 5, we want to first graph 6 to the x. You can make a table of values if you want, that's fine. However, I know this is an exponential growth function because this base is greater than 1. So I know the general shape of it. So I can just real quickly plug in a couple of x values, get a few points plotted, and sketch the rest of the graph because I know what the behavior of this exponential looks like. So if x is 0, then I'm going to be at the y-intercept 0, 1. If x is 1, 6 to the first is just 6. If x is negative 1, then I'm going to be over here at a very small value. And then go ahead and extend off the screen. We have a horizontal asymptote for this exponential at y equals 0. All right, so if I'm going to graph g of x, I'm not going to do a table of values. I'm just going to notice that my x up here as an exponent is negative. That transformation is going to be a reflection across the y-axis. So when x has a negative in front of it, it's a reflection through the vertical or the y-axis. So just think about your y-axis here and creating a mirror image. So this point would coincide with this point. This point stays the same. This point that I have here would come over here. Not too good. And then it kind of goes off the screen this way. We're asked to report the asymptote, domain, and range for g of x. So for the g of x function, we have a horizontal asymptote at y equals 0. The domain for the g of x graph is all real numbers, negative infinity, positive infinity, and the range is going to be from 0 to infinity. Okay, number 6. Let's first graph 5 to the x. So same strategy we used here. When x is 0, we get that same y-intercept. When x is 1, we only go up as high as 5. And when x is -1, we're going to have this very small number over here at x equals -1. So it looks very close to the exponential 6 to the x. All right. So now we're going to study this new equation. So we see that the parent function, f of x, is going to be transformed by being moved left 2. That's associated with this 2 being with x. And then this -1 means we're going to move the graph down 1. So let's just take these 3 key points and move them left 2 and down 1. First thing I might want to do is notice that I'm going to move this graph down 1. So now my horizontal asymptote is going to fall below y equals 0. It's going to fall right here. So let's go back to, this is a good point to start with right here. Let's move this point left 2, let me do it in this color, left 2 and down 1. So this y-intercept has been transformed to here. If I want to draw that part of the graph that goes to the left of that point, it would look like this. Then if I come up here, move this point left 2 and down 1. And then I can draw the other part of the graph off of this y-intercept that's been transformed. So our asymptote is y equals -1. Domain is all real numbers. The range now is going to start at, but not include, -1 and go up to infinity. Number 7, the parent function is e to the x, and then we have some transformations on that. So let's graph e to the x. When x is 0, we have a y-intercept here. When x is 1, we go up to 2.72. You might remember that e is approximated by this decimal. So when x is 1, I'm going to go up close to 3. When I put in a -1 for x on the calculator, that's going to give me a small number. So here's f of x. To graph g of x, we want to be mindful of this +3, which means we're going to move left 3, and be mindful of this part of the equation, which is up 2. So because I am moving this graph right here of the parent function up 2, that tells me that y equals 0, which was my horizontal asymptote of my parent function, is going to be shifted up 2. So I'm just going to go ahead and draw that in. It just kind of helps make sure I put my new graph in the right place. All right, so let's go back to f of x. I'm going to start with this point right here, this y-intercept, and I'm going to move it left 3 and up 2. So this y-intercept is transformed here, which means when I draw to the left here, I have to stay close to y equals 2. Now going back to this point, I'm going to move it left 3 and up 2. So it's not right on a grid mark because it wasn't on a grid mark here. So there's our new function. So what's the equation of our asymptote? Well, it's horizontal, so every horizontal line starts with the equation, starts with y equals. Domain is still all reals, and the range is going to start but not include 2 and go up to infinity. All right, we're going to use this compound interest formula, or this compound interest formula, to find the accumulated value of an investment of $20,000, 6 years, that's your time, at an interest rate of 4%. So the decimal for that is 0.04. So the initial investment, 20,000, was P, so we're finding A. Okay, we're going to compound our interest quarterly, daily, and continuously. Continuously is the word that's associated with APERT, this one right here. So to calculate these two answers, we're going to use this formula. Yes, the formulas will be included in the problems, so you don't have to memorize these formulas. Quarterly means that N is equal to 4. 4 quarters in a year. So I'm finding A, where P is. I'll insert 20,000, parentheses, 1 plus, I got a fraction here, and in the numerator, I'm putting the interest rate as a decimal. The denominator is 4 for quarterly, and my exponent is going to be the product of 4 and 6, 4 times 6. Okay, so just use your scientific calculator. You might want to find this value first, then raise it to the 24th power. That's a multiplication there. And then after you get that answer, then you multiply it by 20,000 last. We're talking money, so we usually go to 2 decimal places. So $25,394.69. Okay, if we're going to compound, same situation, but compound our money daily, that means the number of compoundings a year is 365. So there's 2 places where we need to make a change to 365, and that's in the denominator, and then up here in the exponent for this n and that n. So this is going to be over 365. Close your parenthesis, and then n is 365, and time, the t value is still 6. So if you want to stop and pause and make sure that you're able to calculate these answers on your calculator, that'd probably be a good idea. Sorry, that's a 2. All right, for continuously, we have a change in formulas. Still have $20,000 up front, and then we have a base of E, and we have a product of the rate, which is 0.04, that's R, not N, times T, which is 6. If you're going to do these computations on the calculator, I would suggest find the E key and then raise that to this product. Just be careful, okay, with the parentheses. Hopefully you can see this. I'm going to find the E key on my calculator is above LN, so I'm going to access that. And then here, I'm probably going to do another set of parentheses, okay, and well, there's 2 ways. You can do another set of parentheses here, 0.04 times, well, can I back up? Yeah. If you're using parentheses, okay, to do the multiplication, then you need an additional set of parentheses in the very front and the very back. And this is times 6. Close the parentheses, but you got to close it again. Okay, and then I'm going to go back and multiply this answer, by 20,000. And hope that my answer is similar to my previous ones. Yep, and it is. $25,424.98. Okay, another way to just kind of clean up the parentheses, you don't need parentheses when you multiply 0.04 times 6. I would just maybe do this one set of parentheses, do this multiplication, and we should get the same answer. And then don't forget to multiply by 20,000. And we do get the same answer. Yeah. All right, next objective, let's write each equation in its equivalent exponential form. It doesn't say anything about solving, so I'm just changing the look of this problem, like 1/2 goes to 0.5. If I want to change this log problem to exponential, this is the one where we kind of said around the world. So go to the base on the log, raise it to the y exponent, set it equal to what we call the argument in here, and we're done. Now I'll leave you guys to do this one right here. Okay, let's go back the other way now. Let's take exponentials and change them so they have logs in them. I'll do 11 and leave 12. Okay, so I'm going to start with the exponent, and I'm going to say -2 equals, and I'm going to put log, because I need a log for these objectives. Log of base 5. 5 is the base on the exponential. It should be the base on the log, and then the argument would be 1/125. All right, we've got a group of problems down here where we're asked to evaluate or simplify without using a calculator. So I'm going to go ahead and solve these without a calculator, but no, when you take the exam, you're going to have a scientific calculator, so I don't care. You know, if you want to use your calculator, that's fine. how do we solve these if we didn't have a calculator? Well, we said we would set this problem equal to x, would change to exponential. So 3 raised to the x is 81. We got the same base. So 81 can be rewritten as the power 3 to the 4th. We can remove the bases and we have the answer of 4. If you want to use the calculator and you have that nice little template on your calculator where you can just dump in the 3 and the 81, wonderful. Otherwise, if you're going to use your calculator and not do this work, you'd have to do change of base. Change of base was where we set up a fraction, and on top we did log of the argument, log of the number, divided by log of the base. Oh, there should be a 3 here. We also said it didn't matter what log we use. So if you don't use log, the common log, then you can use the natural log. You could do this as well. Just be careful when you go to your calculator. Parentheses aren't critical in the numerator, but they are in the denominator. So log of 81, close your parentheses, do divide. And here I do an open parenthesis and then I do ln. Dump in your 3, close your parenthesis, and then close another parenthesis for the entire denominator. And I should get 4. Yep, I do. Sorry if that was kind of quick. Okay, right here, by hand, 7 raised to the x equals square root of 7. The issue is you have the square root on the 7. The 7 is the same as this 7, but I need to get rid of that square root. Square root means a 1/2 fractional exponent. Again, you can do this on your calculator. If I did the natural log, it'd be ln of the square root of 7 divided by ln of 7. So if this number's low, the base, then it goes low in the fraction. That might be kind of a good way to memorize that. I see the 3's are the same, but the 3's in the denominator of a fraction, so let's adjust and bring it to the numerator. And when you bring 3 to the numerator, with this understood exponent of 1, we would adjust to a negative. Okay. $25 is bigger than 5, so let's rewrite 25 as 5 squared. Don't forget the power of x. Here what we did is we multiplied those two together to get rid of these parentheses. Maybe write in the understood exponent of 1. Bases are the same. 2x equals 1. Continue solving for x, and you're going to get x equals 1/2. Again, or you can do it on your calculator. 17, by inspection, 2 raised to what power is 2, and this answer will be 1. 18, by inspection, what power does 4 need to have on it so that I get an answer of 1? The only way to get 1 is if you have a power of 0, so that answer is 0. You can do 19 on the calculator, or if you see that an exponential is the inverse of a natural log, a natural exponential is the inverse of a natural log, this answer is just going to be 15. But play it safe, use your calculator to verify. Okay, right here, when I have a natural log function, I might change it to log base e and keep 1 over e. If you want, you can set it equal to x. So e raised to what power is equal to 1 over e. In this situation, which one was it? It was similar to 15. You'd bring e out of the denominator, making it e to the negative 1. So this answer would be x equals negative 1. All right, 21. There's not a base that's present here, but it's the understood base of 10. So these are inverse operations. So think of this as being a power of 1. So log base 10 undoes an exponential of 10. This answer would be 1. Honestly, on that one, just go right to the calculator. Hit log 10. You got an answer. This answer is 7. These two functions undo each other. log base 3 with an exponential base 3, answer square root of 2. If you're not sure about yourself, like I said, just check on the calculator, and this answer is 2. Okay. All right, another objective that we covered for this test was using properties of logs to expand as much as possible, and where possible, evaluate the logs without using a calculator. Okay, but certainly pick your calculator up if you want to. All right, we had 3 properties. We went from product to sum, we went from quotient to difference, and power to factor. So if they're telling me to use properties to expand, okay, I'm going to identify that this is a product in here, 49 times x squared. So a product goes to sum, so log base 7 of 49 plus log base 7 of x squared. We're not done. You might want to go to your calculator, use the change of base, and see that this is 2. 7 squared is 49. Plus, we're not done until we use all the properties possible. Because that's a power, we'll make it a factor by multiplying in front. All right, we're going to expand. This is not a product, this is a quotient, so we're going to go to a difference. So it's log of the numerator minus log of the denominator. So do yourself a favor on your calculator, check to see if that can be simplified. Just do log of 10, and actually that's going to simplify to 1. So we need to record 1 minus log of y. Now I'll come back and do this one later. That's probably one of the more challenging ones. So 28. So we're looking in here at the argument. I see a power. I'm going to put it in front as a factor. I think that's a t base and an x. There's nothing more I can do, so I'm finished. All right, 29, I see a quotient, so that's going to go to difference, but I also see a square root that I'm going to have to handle here in a second. So let's go ahead and do the quotient to difference. So back over here, I'm going to take that square root off and make it a 1/2 power. Now go to your calculator, figure out that 5 cubed is 125, so that log simplifies to 3. But don't leave this term like this. Let's use the power property to a factor. And then we're complete. On 30, I see a product. And that goes to a sum. This term is complete, but this term we need to use the power property. And one more in this section. I see a quotient, I see a power, but I also see this 5th root right here. I need to handle that first. So I've got to get that 5th root off of that quotient. I think I'm going to come over here and rewrite it. So keep the fraction 3 over x to the 4th, but because I'm not going to have the radical, I need to change to a 1/5 power. Had this been a 4th root, this would be 1/4. Had it been a cube root, that would have been a 1/3. Before I do the quotient property or the power property in here, I'm probably going to want to get that 1/5 off of this fraction by using the power property. So pull the 1/5 in front. And I'm going to run out of room, so I'm going to go to the right here. Okay, now I'm ready to do the quotient to difference property. So the 1/5 is going to stay out front. I'm going to do a big bracket here while I do the quotient to difference. Now I'm going to reach inside and look at what I have here. That would simplify to 1 minus Over here, I still can apply the power property by putting the 4 in front. You can leave your answer like this. This would be fine. Okay, or you could distribute in the 1/5. 1/5 times 1 is 1/5 minus, when you multiply 1/5 times this 4 that's up front, it becomes 4/5, and don't forget the rest of the term, log base 3 of x. I'm not sure, just kind of listen in to see how MyMathLab wants you to express your answer, if it wants it, multiplied in or factored out. There should be some suggestion there about how to present your answer. Okay, 31, 32, and 33 has us go just the opposite way. We want to condense. We're going to use properties to condense. Put it back together as a single log expression. So on 31, I see a subtraction, so I'm going to build a quotient. So both terms have a base of 4, so log base 4, fraction bar, 28 is over 7. This will reduce to 4, but we're not done because this value is going to be 1, so that would be your final answer. All right, 32. I don't see any coefficients other than 1 in front of these log expressions. Otherwise, I'd be making those factors of power. I do see a minus. So again, that's another quotient property. Both have log base 5. So 3x plus 2 goes on top and 9 goes on bottom. You cannot divide this 3 with that 9. You have to be able to take out a factor from all terms in a problem. So we're finished. All right, before I use the product to sum, or the sum to product part, before I multiply these two together, the first thing I want to do is I want to get rid of these coefficients by making them powers. So for this first term right here, I'll be left with log base 6. Now this 3x, put it in parentheses and put the square on the parentheses, because you want to square the 3 as well. Oops, I'm supposed to move that up. All right, now that the coefficients are 1, they've been made into powers, I can go and multiply these two arguments together. So you could leave this in this format, or if you want to square 3x, if you want to multiply 3x by itself, you're going to get 9x squared, but then you got to multiply it by y to the 5th. So that would be the answer right here. And you can use parentheses if you want. All right, 34, 35, and 36, it says use common logs or natural logs in a calculator to go to 3 decimals. So just real quick, one setup. This is equal to natural log of 18 over natural log of 16. Calculator work. You can check the key for the answers to make sure you're doing the right keystrokes. Okay, so we'll move down to 37 and 38. I know I'm going a little fast, but you might want to stop the video and just kind of read the directions yourself and kind of plan out in your brain what you think we're going to be doing. That's probably the best thing that you do for yourself in trying to memorize all these different kind of skills. All right, let's solve these exponential equations by getting the same base. All right, I'll do number 38 and leave 37. 343 is a bigger number than this base, so we'll keep 7. So on your calculator, just start multiplying 7 times 7 times 7 until you hit this target number, and I believe that's 7 cubed. Same base, set the exponents equal. Now you have an algebraic equation that you can solve for x and get an answer. All right, 39 and 40, we're still going to solve the exponential equation, but this time we can't get the same base because there's no way to make 9 a power of 2. So we have to use our other strategy we learned, which is to express the solution in terms of common logs or natural logs, and then use a calculator. So what do we do when we can't get the same base? Well, we brought in the natural log on both sides of this equation. We brought in ln here and ln here. The reason we did that is because this x is a problem in the exponent position. So in my next step, I'm going to use the properties of, now that I've made this a log problem, I'm going to move that power to a factor position. So this is x times ln of 2 equals ln of 9. To get x by itself, since I'm multiplying, I will do the inverse operation and divide out ln of 2. So we just got some calculator work to do here. And the result is 3.710. If this third position right here that I'm rounding to is a 0, it needs to be present. Otherwise, if you don't put that 0, it might look like to somebody that you just rounded to the hundredths and not the thousandths. Okay. So we'll finish the rest of the review in the next video.